Hi, everyone. Hope your week is going well. It turns out I was a bit ambitious in our third and fourth discussion sections. I thought we could get through more problems than we did. So just to make sure we get through what I said we'd get through, I'm just recording a video. And yeah, you're not required to watch it, but if you want to, here it is. So let's start going through. So section 1.3 was back in quantified statements. This is all stuff to deal with universal and existential quantifiers, the for all and their exist symbols. And I think I went through a couple of these with you guys, or a couple similar ones. But all we want to know here is which statements are true. Okay, so let's think through these. If we think it's true, maybe we can write a sketch of a proof. If we think it's false, maybe we can negate the statement and show why it's false. Provide a counterexample, maybe. Okay, so let's look at part A. Part A says, and keep in mind we're dealing with the real numbers here. So part A says, for all x, there exists a y such that x plus y equals 0. I think we did this one in section. I think it actually appears in a later part of the book, and they ask you to prove it. Here they're just asking if it's true or not. We can say true. The logic is, okay, so I'm not going to write the full proof out, but we could just say pick y equal to negative x. So if y is negative x, those two things cancel and we get 0. So that's a true statement. But what happens if I swap those two, right? So I make it, there exists an x such that for all y, x plus y equals 0. Well, maybe take a minute to think. I'm going to say false. Okay. And maybe we'll provide justification why it's false. Or actually, if it's false, its negation must be true, right? So let's see what its negation looks like. Maybe I'll put a little negation symbol out front. Maybe I'll put that over here. Negation of there exists x such that for all y, x plus y equals 0. Okay, here we have to recall how to negate quantifiers. So just a little side note to ourselves. The negation of some statement like this, for all x, some predicate holds, would be there exists an x such that the predicate does not hold. It's supposed to be a p. And then similarly, the negation of there exists an x such that a predicate holds would be for all x, the predicate fails. So negation of p. Okay, so with that, we can negate this whole statement. Okay, so negating the whole thing, the there exists would change to a for all. And then maybe I'll go one step at a time. So we're negating this whole thing, which is sort of like saying we're negating a there exists statement where this is the predicate. So it's p of x. Okay, so that would look like for all x, not p of x. So not. And then I'll just sketch down what p of x looks like. Okay, but then this negation can be applied as well. And that for all will swap to a there exists. Okay, so I'll keep the outside the same. And then when I factor this negation symbol in, I'll get a there exists. Sorry, there exists y such that, okay, and now I'm negating the predicate. But the negation of x plus y equals 0 is just If I copy the rest down, x plus y is not equal to 0. Okay, so all that is to say, the negation, switch colors really quickly, the negation of this statement is this statement. And so if we think our original statement is true, right, so if this is our original statement, or sorry, if we think the original statement is false, the negation must be true, and vice versa. So let's think about this now. Is this a true statement? For all real numbers x, there exists a real number y, such that if I add them together, I don't get 0. That is true, right? I could say, okay, pick any real number x. And then, yeah, we could always find a y that's not going to cancel with it. Can I write down an exact one? Maybe not. But yeah, copy. Yeah, you could maybe come up with some examples. I mean, if x was 5, for example, I could pick y equals 2 or something, right? As long as I don't pick, the only thing I'm not allowed to pick is its additive inverse, right? Literally any other real number would be fine. So that's not exactly a proof, but we're not tasked with getting a proof here. We're just wondering which statements are true. Okay, so the negation of this statement is true, meaning the whole statement, right? The statement originally must have been false. It's not true that there exists some real number such that all real numbers cancel with it. That would be nonsense, right? Every real number has a unique additive inverse. It's not possible for every real number to be an additive inverse of a given x. Okay, so that's a mouthful, but that's how you would go about showing it. So just to, I'm going to erase this and write a shorter version, just so we can have, give it 1 second to respond. It's freezing up. I'm just going to write what the negation of this statement looks like, because that's a useful thing to be able to reproduce. Okay. Just finish cleaning this up. Okay. So the negation of that was for all x, there exists a y such that x plus y is not equal to 0. Once you get used to negating these quantifiers, it's going to get easier to just go straight from this step to this step without writing all the intermediary steps. Okay, so let's go on ahead. Part C, there exists an x and there exists a y such that x squared plus y squared equals -1. Okay, when you see existent statements, the first thing I always like to do is try to imagine what numbers might work to satisfy the given condition. So I could try any numbers I wanted to, right? My real number, or my universe is the real numbers. So I could pick positive or negative or 0 or irrational or rational numbers. I could go crazy, right? As long as I don't do anything with complex numbers, I guess I'm safe. But no matter how hard I try, I'm probably not going to be able to do that. Find two numbers whose squares add up to a negative number. So again, I might suspect this is false. And if it's false, its negation must be true. So let's think about what its negation looks like. So I'm negating this whole statement. Okay, negation of there exists is for all. So I'll say for all x and for all y, and then just negate this statement here. So instead of x squared plus y squared equals -1, say not equal -1. And then I'll ask, is this a true statement? And the answer would be yes. This is saying, okay, for all real numbers x and y, the sum of their squares is not -1. And that's true. Again, maybe you could sketch a tiny proof and be like, okay, x squared is positive, y squared, I guess I'll say greater than or equal to 0. Y squared is greater than or equal to 0. Therefore, their sum is greater than or equal to 0. So definitely cannot be equal to -1. Okay, so I'll erase that. And we're confident this is a false statement now. If you haven't noticed, I'm putting the true statements in green and the false statements in red. All right, part H, this is our, there exists a unique element of the real numbers, which we're calling y. So the exclamation point means uniqueness. Okay, so this is claiming there is a unique y such that these two things hold. Y is less than 0 and y plus 3 is greater than 0. Okay, for a unique existence statement to be true, you would need to show two things. One, first of all, there exists a y such that that property holds. Just call it p of x for now. And two, you would need to show that, we'll say for all x where p of x holds, that ends up implying that x is actually the same number as y. That would imply uniqueness, right? If the set of all things where this property holds ends up just being the number y, then we have uniqueness. Okay, so let's go through and try to show each of these things. Let's show that, sorry, my screen keeps flickering in and out. Let's go through and try to show those things. Okay, can I find some real number y that satisfies this? Well, the first condition means it has to be negative, so maybe we'll try -1. Does -1 satisfy the second condition? Well, yeah, -1 plus 3 is positive, so it's greater than 0. Cool, okay, so this works. So that satisfies that first condition, that there exists some number that satisfies the condition. Now I have to show it's the only number. Well, if you think a little bit harder about it, what if I had picked -2? Right? -2 satisfies the first condition. It also satisfies the second condition. So actually, it's a false statement. Surprise, surprise, I was using red for a reason. Okay. And that's a sufficient, I mean, it's not a well-written proof, but again, I'm not proving things here. I'm just making some argument why they're true or false. Okay, so the fact that two numbers exist satisfying this condition means uniqueness fails. So the statement there is a unique y such that y is negative and y plus 3 is positive is false. So I'll say, for example, both of those work. Actually, there are infinitely many real numbers that work. So there we go. All right, next uniqueness statement, part I. How about there exists a unique real number x such that for all y, x equals y squared. Okay, this one's a little weirder to think about. There exists a unique real number x with the property that all numbers y satisfy this equation. When I phrase it like that, it sounds false. Okay, so let's negate it and see if it sounds better. Okay, negating a unique existence claim is going to be a little interesting. Okay, actually, it's quite a bit of work. So the original claim, there exists a unique x with some property, means there's only one element in the truth set. The opposite of that could be two things, right? It could be there are 0 elements in the truth set, or there are multiple elements in the truth set, which is similar to what we had here, right? That unique existence statement failed because there were multiple elements in the truth set. Here, I'm thinking we're going to get no elements in the truth set. So maybe rather than going through all the work of negating this, I'll just say false. Because, let's see, what's the best way to phrase this? Actually, yeah, okay. We can negate something simpler, make our lives easier. What if I just had this statement? What if I just had the statement, there exists an x such that for all y, x equals y squared. Okay, so that's simplifying a bit. I've removed the uniqueness claim, but let's negate that and see what happens. So the negation there would be for all x, there exists a y such that x is not equal to y squared. That's definitely a true claim, right? For all real numbers x, so I'm allowed to pick some real number x. Can I find a y such that this equation fails? I mean, yeah, definitely. Like just to see an example, okay, what if I pick x equals 1? Then what could I pick for y to make that equation fail? I don't know, 2, right? 1 is not equal to 2 squared. And you can probably convince yourself no matter what I pick for x, I can always do that. Okay, so erase that. So here we're saying it's false. So the simplified expression, right, kind of removing this uniqueness assumption means, okay, so if I just X that out, this statement would be false. And if that statement is false, definitely the uniqueness statement is false. Because if we're saying there doesn't exist an X with this property, there definitely doesn't exist a unique X with that property, right? There are no X's with that property. Okay, so that's kind of a workaround way to get to that solution. And again, all this stuff I'm writing is not actually required, but trying to justify why things are true, just so you get a feel for how that works in the future. All right, let's look at J. So J says, for all y, there's a unique x such that x equals y squared. Okay, that's a little more interesting. So whatever number I pick for y, this statement has to be true. A uniqueness claim saying y squared equals x. But that should be true, right? This equation here, if I pick a value for y, it's going to spit out a value for x, and that value of x isn't going to change. So that should be true. Okay, I'm not going to spend a whole lot of time justifying that like I have been. Let me erase this. But hopefully that's clear. And then the final one, there exist unique x and unique y such that for all real numbers w, w squared is greater than x minus y. That's an interesting one. So maybe we'll take a minute to parse that. I'm saying there's a unique pair of real numbers, x and y, such that x, well, maybe I'll flip this inequality and say x minus y is always less than w squared. And maybe phrased like that, you see it's false. Because, okay, let's show there are multiple pairs of real numbers I could pick here. So let's try like let's first show one pair works. Maybe I could pick x equals -1, y equals 0. Right, so this is -1 minus 0, which is -1. And you should definitely be convinced that w squared is greater than -1, no matter what value I pick for w. Right? A real number squared is always non-negative. Okay, but with that train of thought, you could be like, wait, I could have picked something even more negative for x. Or I could have picked, x equals 1 and y equals -10. Anything to make this side of the inequality negative. So it's definitely false that there are unique numbers. There are numbers, x and y, satisfying this property, but it's not unique. Okay, cool. So that's our little warm up. After this, we want to actually write proofs for these things. After section 1.3, I think there's one more problem we could work on in section 1.3. Yeah, here we go. This is another good one. So here we're given 4 sets of numbers, 4 sets containing numbers. So T is the set containing 17, just the number 17. U is the number containing, or the set containing the number 6. V has 24 in it. W has a bunch of things. Okay. Cool. And then the questions have to do with which of these existence and for all claims end up being true. Okay, so let's think about this. And in which universes, I should say. So these are universes. In which universes do these statements hold? Maybe none of them, maybe all of them, maybe some. So let's work through it. Here we have there exists an X. So which universe is it true that there exists an X where this implication is true? Okay, so let's think through it one at a time. How about T? Does T work? Well, the only element in T is 17. And does 17 satisfy this implication? Well, 17's odd, and 17's greater than 8. So yeah, that works. Okay, so I'll say T checks out. How about the set U? Okay, so you probably look at U and you're like, oh, there are no odd numbers, so it's going to fail. But let's go through it logically. Okay, there exists an X in the universe U such that this holds. Okay, so first of all, there does exist an element X in U. Right, 6 is in U. And then does 6 satisfy this implication? Well, 6 is not odd. And similarly, 6 is not greater than 8. But, right, this is one of those weird things. What happens when you have false implying something? A false antecedent is always true. So, weirdly, this is actually a true statement. Okay, so U is a universe where this works, where that statement is true. There exists an X satisfying this implication is weirdly correct. Okay. Now you see why I wrote it all out. It's a bit of a thinker. Right, how about V then? V should be the same story, right? V, I'll get, well, 24 is not odd. 24 is greater than 8, but the consequent doesn't really matter. The fact that I have a false supposition here means the whole statement is true. So V works for sort of the same logic. And then how about W? So W says, okay, there exists an X such that X is odd implies X is greater than 8. That should work. W contains, well, it has these 3 numbers, Actually, let's break it up. We have a couple odds. Right, those are odd. So let's take 3, for example. So we'll set x equal to 3. So x is odd, yes. But is x greater than 8? No. Okay, and true implying false is overall false. Okay, so 3 doesn't satisfy it, nor does 7 for the same logic. However, 2 and 26 do satisfy. So 2 and 26 are elements of W such that they're not odd, and depending on which one you pick, it might be greater than 8 or it might not be. But that gives me a true result. And so weirdly, W also works. Even though W contains no odd numbers greater than 8, it's still satisfied. Weird. Okay, so you really have to think these things through in detail. Sometimes, don't trust your intuition. Whoops, shouldn't have erased all that. It's 2, 3, 7, 26. Cool. The next view should be easier. So how about this one? So again, our claims here relate to the oddness and the factor, the claim that it's greater than 8. Right? That's the same for actually all of these. All we're changing is whether it's a there exists statement or a for all statement, and whether the condition here has an and or an implies. So that changes the result quite drastically, as we'll see. So part B says there exists an x such that x is odd and x is greater than 8. So this is more in line with probably what you were thinking when I read part A. Okay. So is it true for T? There exists an element of this universe where x is odd and it's greater than 8. Yeah, 17 works, right? So that's still true. How about for U? Well, is there an element of U? Well, the only element is 6, right? Such that both of these are true? Actually, no, neither of them are true, right? 6 is not odd, 6 is not greater than 8. So this and that fails. Okay, so U is not included. It's not one of the universes where that statement's true. And it quickly becomes apparent the only universes where it's true are the universes where you have an odd number greater than 8. So V fails. There are no odd numbers greater than 8 in V, and there are no odd numbers greater than 8 in W either. So it's actually only T for that one, which is, like I said, probably what you were expecting for part A, but part A tricked us with this implication sign. Implications behave pretty weirdly. All right. How about part C then? Part C, which universe is it true that for all x in the universe, x being odd implies x is greater than 8. Okay, let's look at T. Again, 17 is the only element in T. So is it true that this statement would hold for the number 17? Well, yes, I mean, it's been holding this whole time, right? So T works. How about for U? So U, the only option I have is 6. And is this a true implication for the number 6? Again, weirdly it is, because the antecedent fails to be true. 6 is not odd, but false always implies true. So there we go. U satisfies it. For the same reason V satisfies it. And then interesting question, does it work for W? Okay, W, is it true that for all x in W, this statement holds? Okay, well, if it's true for all x, it would have to hold for, say, 2. Okay, so 2 works, right? 2 is odd, does imply 2 is greater than 8, because 2 is not odd. Okay, it would have to work for 3, so let's check 3. Okay, 3 is odd. 3 is odd, implies 3 is greater than 8. So which pieces here are true? Well, 3 is odd is a true statement. 3 is greater than 8 is a false statement. And true does not imply false. Okay, so W actually fails. Right? 3 ruins it for us. 7 ruins it for us. So there, we don't get to write W. Oops. W is not a universe where statement C, part C holds. Right, how about for all X? X is odd and X is greater than 8. Okay, T works. Right, 17 is odd and greater than 8. U fails because 6 is not odd or greater than 8. V fails because 24 is not odd. And then W fails because it would have to work for all X and W. But there are definitely elements in W that are even. And there are also elements in W that are less than or equal to 8. So that's that. T is the only place that works. Okay, and so that's our warm-up done. Hopefully that stressed your brain out a little bit. It's definitely a weird one. Now we're going to do some proofs. So let's jump ahead. Go to section 1.4. This is one I didn't have time to work on, so let's do it now. All right, in problem 5, oops. In problem 5, I'm working in the universe of integers, and I'm saying if X and Y are odd integers, their product is odd. Okay, we saw a couple proofs like this in section. So I advise you to pause the video here and try to do it yourself. You should be able to by this point. So pause and then come back. The proof should look something like this. I'll say let X and Y be odd integers. Then what does that mean? Well, it means that X can be written as 2n plus 1, and Y can be written as 2m plus 1, where n and m are just some integers. So X and Y are multiples of 2 plus 1. So they're 1 plus an even number, meaning they're odd. Okay, and then I could say, well, what does X times Y look like? That would be 2n plus 1, just substituting in. And then foiling, I get 4nm plus 2n plus 2m plus 1. And my goal is to show that that product is odd. For that product to be odd, it would have to look like 2 times an integer plus 1. So can I write this as 2 times an integer plus 1? Well, yeah, I can factor a 2 out of these first 3 terms. And so pulling a 2 out of the first term gives me that. Second term just give me an n. The third term would just give me an m. Then I'll close my parentheses and tack that plus 1 on the end. So that's definitely an integer. So I'll just say that's in Z. And so that is XY is odd. QED, put a little box on the end, whatever you like to do. Great, so that's similar enough that hopefully that makes sense and hopefully you got it on your own. Let's keep forging ahead. Okay, so 1.6 is all about proofs involving quantifiers. So I did 4b in section, but let's do 4f. This one, it says, provide either a proof or a counterexample. So it's not telling us whether the claim is true or false. So here I've just written a claim. We'll have to decide for ourselves if it's true or false. Okay, the claim is for all positive real numbers x, this holds. Okay. maybe we think it's true, right? Because like x squared is definitely positive. And maybe you're thinking, oh, if I like take 2 and I square it, it gets bigger, right? Or if I take 10 and I square it, it gets much bigger. So like x squared minus x, yeah, maybe it makes sense for that to be positive. Okay, so you might try for a while to prove this, but you would struggle a lot because it's false. Okay, so I'm going to claim it's false. Because the negation looks like this. Actually, before I write the negation, let me translate this. Okay, so the claim is really, I could write it like this. For all x in R, so for all real numbers x, the following holds. Notice we're restricting to positive numbers. So I could say x greater than 0 implies the result. 0. Okay. There are other ways you could write this, but that works. This is sort of like saying for all x that are positive, the result holds. This is sort of a restriction on the universe we're working in. Oops. Okay, the negation then looks like this. Well, the negation would say there exists a real number x such that, okay, and then you have to remember how to negate an implication. So let me write a note to myself. We do know that P implies Q is the same as equivalent to not P or Q. So if I wanted to negate this, it would be the same as negating not P or Q, just negating that part. And the negation there, I can use De Morgan's law, and that would be P and not Q. Okay, so that's what the negation of an implication looks like. So negating this implication, sort of like this is P, this is Q, right? Would look like x is greater than 0 and not this. Whoops, I had this written wrong to start with. Sorry about that. I put a squared here when I shouldn't have, but hopefully you guys saw that and wrote it correctly. So here we have, okay, the negation of this statement would be x squared minus x less than 0. Just swap that inequality sign. Okay, so that's my negation. So if I'm saying the claim is false, the negation has to be true. So essentially, I'm going to exhibit a counterexample. So the counterexample comes from picking a number x that satisfies both of these things. And the value of x I can pick is just x equals 1/2. Because if x equals 1/2, then we get 1/2 is definitely greater than 0, so that checks out. And 1/2 squared minus 1/2. Well, that's a quarter minus a half, which is negative a quarter, is less than 0. So that checks out as well. Cool. So yeah, you could have picked any number between 0 and 1 inclusive, and that would have worked out. 1/2 was a nice one to work with. So that's really all you have to do. Maybe you could write a sentence explaining that. Say, you know, if we choose the real number x equals 1/2, then both of these hold. Therefore, the negation of the statement is true. Therefore, the claim itself was false. Okay, but I'm a bit lazy. This video is running longer than intended, so I'm just going to skip ahead. And let's do the next one. Okay, 1.7. kind of brings everything together. So let's try to tackle this one. Okay, this looks like it's a bit backwards. I would actually write this the other way around. I would take each of these and swap them. Say for all for all integers n, the sum is even. But it's fine to write it that way. I think they're trying to expose you to a bunch of different ways of writing mathematical theorems. All right, so let's prove this. First, we'll note maybe we'll break it into pieces and show that each of them is even. That would be helpful, right? So what I could do here is I could say, well, okay, we have to show it for all integers. So you would have to break this up into pieces, right? So I would have, I'm just going to show you the steps. I'll let you guys fill in the blanks. How about that? So step one would be something like, let me think about this for a second. I was gonna say something which I'm not sure is true, so I want to check I wrote this down correctly. This is 3a. Yeah, that does hold. Okay. Yeah, so this is a little problematic. So what I'm thinking about is it true that each of these pieces is even? If each of the pieces is even, we know a sum of even numbers is even, so that would be fine. 4 is definitely even. 3 times n, though, might not be. And similarly, 5 times n squared might not be. So we'll have to get a little creative. You could do a proof by cases if you wanted to, so a proof by exhaustion. Or maybe we could simplify this thing a little. I don't know if this will help, but maybe I'll pull an n out of the first two terms. Right, so I could write that expression as such, n times 5n plus 3 plus 4. And then if I could argue that this piece is always even, I would be fine. And yeah, I think you'll have to do a proof by cases in either event. So maybe that's what I'll say here then. I'll say, I'll start by saying n is either even or odd. And then we'll break into cases. Case 1, we'll say n even. Case 2, n is odd. And maybe I'll just do one of these. I'll do the odd case for you guys. So we'll have, or actually, yeah, I'll do even. I'll do even because that's easier. So I want to look at each of these pieces. Okay, if, say, let n be an even integer, then n is going to be 2 times k. K is just any old integer that works for that. Okay. So I could write, again, I want to investigate each of these pieces separately. Yeah, so I could say 5n squared would be 5 times 2k squared, which would be 5 times that quantity, which is 20k squared. Okay. And then we could make an argument that that's even because that's 2 times some integer. Okay. Similarly, 3 times n is 3 times 2k which is 2 times 3k. That's also 2 times some integer. And so I could say that is 5n squared and 3n are even. Okay, I'll let you guys finish that because I've run out of room. But the next thing you would say is 5n squared plus 3n is even by one of the theorems we proved previously. And if you've proved something before, you're allowed to use it again. And then adding another even number, again, applying that old theorem, the result ends up being even. Okay, then you would have to show it for what if n is odd. It'll still work. It's just a bit more algebra. It's not harder, it's just more algebra. So I'll leave that one to you guys. It's good old proof by cases. How about this one? For all integers, if 5n plus 1 is even, then this expression is odd. Okay, this is a good one to try on your own. So pause the video if you would like, and I'll wait a second and get started. All right, so let's prove this. To prove it, I'll start as always. Whenever you see a for all, the first line of your proof should be, okay, suppose that part's true. And by that, I mean, let's pick some arbitrary natural number, or sorry, I keep saying natural number when it's an n, some arbitrary integer n, and let's work with it. So this is some statement, if p, then q. Okay. So, yeah, let's work with the statement p. So I'll say note that it's a good thing to do here. All right, so we can assume that this holds. All right, so we'll say, suppose five n plus 1 is even. Okay. What does that mean? So let's think about some cases where 5n plus 1 is even. Like, let's think of some numbers n that could make that even. Well, so here this is my thought bubble. Thinking to myself, what about n equals 0? Does that work? Well, that would be 5 times 0 plus 1, which is 1, so it doesn't work. What about n equals 1? Well, 5 times 1 plus 1 is 6, so that does work. That's good. What about n equals 2? That would give me 11, which doesn't work. But n equals 3, that would be 15 plus 1, so that's 16 is even. N equals 4, it's 21, not even. N equals 5, hopefully you're seeing a pattern here. N equals 6 fails. This only works if n is odd. Okay, so let's write that down. Technically, we'd have to prove that. Okay, so let's see. I could say, what's the best way to write this? Yeah, we could say, well, maybe I'll do a mini proof by contradiction. Suppose n is even. That was the bad case. Those were all the things I crossed out. If n is even, then 5n is even, right? Because we proved, again, in a previous exercise that an even number times any integer is even. But then adding 1 to it will make it odd. This contradicts our assumption, right? So n cannot be even. Let's say FTSOC, which is for the sake of contradiction. So this contradiction implies that n is actually odd. Okay, so that's kind of a mini proof inside this larger proof. All right, and now we know that n is odd. So we would have to go about, okay, maybe I'll say it remains to show that 2n squared plus 3n plus 4 is odd whenever n is odd. And I think you guys should be able to handle that. I'll just say n being odd implies n equals 2k plus 1 for some integer k. And then you could just write out, substitute 2k plus 1 for all the n's. And then you guys should be able to make quick work of why that expression is odd. But a little bit of algebra involved. You want to make it look like 2 times an integer plus 1. It takes a bit of work, but I think you can handle it. All right, so skipping ahead. We're just doing a blitzkrieg at this point. This is a fun one. The sum of 5 consecutive integers is always divisible by 5. Okay, the way I would start this, they don't tell us what particular integers we're working with, right? So that's a little weird, but I could just say let n be an integer, right? Because they're sort of saying for any n you pick, n plus the next 4 integers always has this property. So pick some, right? Pick an arbitrary integer, call it n. Then the consecutive integers would be, well, the sum of the consecutive integers would be n plus 1 would be the next one. N plus 2 would be the next one, n plus 3 after that, and then n plus 4. I don't need parentheses here, obviously. I'm just showing these are the 5 consecutive integers we're working with. Okay, and then I'll add all the n's up. That would be 5n. And then if I add 1, 2, 3, 4, that gives me 10. Simplifying, that's 5 times n plus 2. So I'll say that is the sum is a multiple of 5 which is the same as saying it's divisible by 5. It's a multiple of, it's 5 times an integer, I should say. Right, it's good to mention here that this piece is an integer. But that's pretty much sufficient. Tombstone. All right, and then this one will be our coup de grace. I like this one a lot. So you guys haven't seen much about irrational numbers yet. As far as you're concerned, irrational should just mean not rational. And I explained what rational numbers were in section. All right, so let's write what rational numbers are. So I'll write a remark, or maybe recall, that Q was the set of rational numbers, and the set of rational numbers was all things of the form A over B, such that A and B were integers, B was non-zero, and there was this weird third condition, which sometimes you'll see the greatest common divisor of the numerator and denominator is 1, which is basically a fancy way of saying the fraction is in reduced form. think about that a while to figure out why that is. But that's a condition to be in Q. To be a rational number, you have to be, so 4/6, I would have to reduce that to 2/3 if I wanted to say it's an element of Q. So what does that mean for us? Well, if x plus y, oops, I don't have my eraser on. We're trying to prove this statement, and I'm going to claim rational numbers are easier to work with than irrational. This isn't part of my proof, just noting this to myself. Right, we know the definition of rational. The definition of irrational is just the opposite of this, which is like a weird thing to talk about. So maybe that hints to you I could try a proof by contradiction. Okay, so let's do that. I'll say, okay. We're always going to assume this part's true. So let x plus y. And here I'll just say, instead of writing, let it be irrational, I'll say, let it not be an element of Q. Because you're either in Q or you're not. If you're in Q, you're rational. If you're not in Q, you're irrational. So that's a fine thing to write. And then suppose, for the sake of contradiction, so that's my shorthand. Not everybody uses that, by the way. So it's probably better for you guys to write that whole phrase out. Suppose for the sake of contradiction that the negation of this statement holds. So what's the negation of x or y is irrational? The negation would be x and y are rational. And maybe you want to write why that's true, that I can negate this statement. But recall that the negation of an or is an and, where each of the pieces is negated. So instead of either one being irrational, they're both rational. Okay. So what does that mean? To be rational, it means these things are satisfied. So I could write x equals a over b, y equals, I don't know, some other letters, maybe p over q. And then here I'll just say, okay, again, a and b are integers, b is non-zero, it's in reduced form. Same story here, p and q are integers where q is non-zero, and it's in reduced form. Now, keep in mind, I'm doing this for the sake of contradiction, meaning I want to reach something absurd. So goal is deduce an absurdity. Okay. The absurdity is probably going to look like the opposite of our assumption here. So with that in mind, let's look at x plus y. X plus y would be, okay, a over b plus p over q, which have different denominators, but let's get similar denominators. So that would be aq plus bp over bq. And I want to argue, so I'll put this in red, I want to argue that this is in Q. How could I do that? Well, to be in Q, we have to satisfy three things. The numerator and denominator have to be integers, and you could successfully argue that. AQ is an integer, BP is an integer, their sum must be an integer. Similarly, B times Q, that's the product of two integers, so it must be an integer. Okay, so that part isn't too bad. We would have to argue the denominator is non-zero. Well, what's the only way BQ could be 0? Well, actually, there are two ways. Either B could be 0 or Q could be 0, but we've claimed otherwise. Okay, so we could say, that checks out as well. So each of those check out. And then it's a bit more work to show that the greatest common divisor of these two is 1. Right, so I would need to show GCD AQ plus BP and BQ is 1, which is a bit of work, but that's the gist. So we'll put a tack in it, and yeah, I look forward to seeing you guys next week. I'm gonna go eat lunch. Hopefully this was helpful. Just seeing some more proof techniques. And yeah, let me know if you have any questions.